Now, what I think I'll do for the next couple of days is I'll leave some time for you to ask questions. I think I'm okay time-wise, but it kind of depends when I say okay, because I could do a lot of those curve sketching problems, and they really could take up a lot of time. Okay. Now, as far as my minimum standard, I guess you could say, of getting through the lecture is I can finish 4.7 by this week. So that should be not that hard to do, which means I only have a 4.8 left for Monday and Tuesday, and that should be about it. Okay, so if I finish everything by Tuesday, I'm aiming to finish by Tuesday. Wednesday's Veterans Day, Thursday question and answer, and then Friday's the test. Okay. This Friday, I'm very much leaning toward letting you have almost the entire class period for one good curve sketch. Okay, where I'll give you just one problem. You analyze the whole works, okay, in terms of domain, intercepts, symmetry, asymptotes. You don't have to write anything down. I'll write it for you, but it's in the guidelines for section 5 again. And then intervals of increase and decrease, max and min, concave up, concave down, inflection points, and then graph it. Okay, so Friday, I'm going to let you have most, maybe even the entire class period. I'll decide by the time tomorrow's over, see how far I get. Okay, so for today, I was going to do some more of the applied max-min problems, 4.7. Then after a certain period, I'll stop and let you ask questions on any previous section. I'm guessing you might want me to do some curve sketches, but you can ask anything from before. And same thing for tomorrow, for Thursday. Okay. All right. So let me go back and do some more of the many word problems that we had. So again, I've decided to throw one problem out. 18. I think 18 was originally listed. Okay. A little part of it that I don't like, so skip 18. So 3, 4, 7, 8, 11, 14, 15, 21, 25, 37. Okay, so I did some last time. Let me try to do more. Okay, so I'll start off with problem number 4. Okay, the sum of two positive numbers is 16. Okay, so I call it x and y. X plus y equals 16. X is greater than 0. Y is greater than 0. Okay. So what is the smallest possible value for the sum of their squares? Sum of the squares means x squared plus y squared. And that's what you're trying to minimize. Okay, so again, sum of two positive numbers is 16. X plus y is 16. X is greater than 0. Y is greater than 0. Okay. The sum of the squares means x squared plus y squared. You're trying to minimize that quantity. Okay. All right, so again, right now I have two variables. Get it down to a single variable. Okay. Normally, when you have something like this, get rid of the variable that isn't x. Okay. Isolate the variable that isn't x, y. Y is equal to 16 minus x. Now, the reason why you do that is now when I substitute in for x squared plus y squared, x squared plus y squared, now I have my expression, I'm going to call it f of x, which is only involving x. And I'm trying to minimize this quantity now. So there it is. Minimize this with the restriction that x is greater than 0. And of course, that means y is greater than 0. Okay, so x squared plus y, here's y, based on this. Okay, so a lot of these problems, you start off with two variables, like x and y, or L and W, or something like that. Try to get it down to a single variable. Okay, so f prime of x, 2x, plus 2 parentheses 16 minus x to the first power times the derivative of the inside, which is -1. Okay, I'm going to clean this up. The negative of 16 minus x is x minus 16. That's the same as that. Okay, and then that's 4x minus 32. F double prime is 4. That's greater than 0. That means concave up. So if the derivative is 0, I will have a minimum. And that's what I'm looking for. I'm looking for a minimum. Okay. And by the way, the book won't trick you, and I won't try to trick you either. Like, if it's supposed to be a maximum, it doesn't come out to be a minimum, or vice versa. Okay, we're looking for a minimum. It'll usually turn out to be a minimum if you do everything right. Okay, so second derivative greater than 0 means concave up at a horizontal tangent. I have a minimum. Okay, so set f prime equal to 0. That's pretty easy. 4x minus 32 equals 0. X equals 8. So if x is 8, what does it mean? Y, 16 minus 8, also 8. So the two numbers are 8 and 8. But go back and answer the question. The question is, what is the smallest possible value of the sum of their squares? So you actually have to come up with the sum of the squares. So that's easy. X squared plus y squared is 8 squared plus 8 squared. 64 plus 64 is 128. So the final answer for this problem is 128. That's the smallest value for the sum of the squares. Okay. All right. Okay, so that's that one. Next one I was going to show you is number 8. This out and show you the book. Yeah, the book's real heavy. Find the dimensions of a rectangle whose area is 1,000 meters squared, whose perimeter is as small as possible. Okay, so you're trying to minimize the perimeter. You have to have this much area. Okay. So minimize perimeter, maybe it's fencing. So you want to minimize the fencing, of course. All right, so I drew myself this picture. Rectangle, x by y. The area is 1,000 meters squared, sorry, not meters squared. So you have to have 1,000 meters squared, and you're trying to minimize the perimeter, it says. Perimeter is as small as possible. So minimize the perimeter. Perimeter of a rectangle is 2x plus 2y. Okay. So let me reuse the book. Getting a workout just carrying this book around. All right, x times y is 1,000 meters squared. Minimize 2x plus 2y. So how do I get it down to a single variable? Okay. Try to isolate the variable which is not x, y. That's easy. Y is equal to 1,000 over x. Then I pick that up and plug it right into there. So notice by doing this technique, you now have a function that only involves one letter, x. And that's what we usually prefer. We prefer to have only in terms of x. I could do it with y, but we don't want to. So perimeter, I'll call it P of x now, is 2x plus 2y. And we now have y as 1,000 over x. So I have 2x plus 2,000 x to the negative 1. So there it is. And I'm trying to minimize this quantity. So I usually write down min this or max this as a verb, minimize or maximize this quantity, with the restriction that x is greater than 0. If these are distances, distances are never negative. Okay, so if I get a negative answer or 0 even, throw it out. You can't even have 0, right? If x is 0, you don't have a rectangle. All right, this is better for taking the derivative. Okay, I got to go back up the paper. Now for the derivative is 2 minus 2,000 x to the negative 2. Agreed? Okay, so I've said it. Now let me show it to you here. 2 minus 2,000 x to the negative 2. That's better for algebra. Sorry, that's better for calculus, but for algebra, it's better to have it like this. Then I do the second derivative. So what's the derivative of this? Derivative of 2 is 0. Negative 2 times negative 2,000 is positive 4,000 x to the negative third. Which I'm going to write like that. 4,000 over x cubed. And I already know x is positive, right? 4,000 over x cubed is definitely greater than 0 for all x greater than 0. Okay? And for this word problem, I'm only allowed to plug in positive stuff. If x is any positive number, 4,000 divided by x cubed is greater than 0. Second derivative greater than 0 means concave up, and it means I have a minimum. Am I looking for a minimum? Yes, I'm looking for a minimum. Okay, so set p prime equal to 0. 2 minus 2,000 over x squared equals 0. Multiply both sides by x squared. 0 times x squared is 0. 2x squared minus 2,000 equals 0. Factor out of 2. X squared minus 1,000 equals 0. That means x squared minus 1,000 is 0. Move over the 1,000. X squared equals 1,000. X equals square root of 1,000, which is 10 radical 10. Plug back in. Y is 1,000 over x. So y is 1,000 divided by square root of 1,000, which happens also to be square root of 1,000, or 10 radical 10. Okay. So it asks for the dimensions in the problem. Find the dimensions. So the dimensions are 10 radical 10 by 10 radical 10 meters, i.e., just as we anticipated, it should be a square. And we've already talked about that before. Okay. If you have a given amount of area for a rectangle, it must be a rectangle. To minimize the perimeter, you would make it into a square. So 10 radical 10 by 10 radical 10. So there we go. Okay, so that's that one. The next one I want to show you is well, I think I did 15, but I'll go over it again. I've gone over it quickly. 12,000 centimeters squared of material is available to make a box with a square base and an open top. Find the largest possible volume of the box. Okay, so we talked about the box already. Okay, so the picture looks like this. Square base, open top, x by x by y. Surface area, they told me, is 1,200 centimeters squared. And you want to maximize the volume. So the volume is x squared times y. Okay. And I mentioned yesterday, just like problem 14, you have 5 faces, front and back, left and right, and the bottom, but no top. So the total surface area is 4xy for the 4 sides, okay, the front and the back and the left and the right. And the bottom was x squared. That's equal to 1,200. Okay, solve for y. Subtract x squared, divide by 4x. So y is equal to 1,200 minus x squared all over 4x. And that gets substituted right over there. So the volume as a function of x now, v of x, is x squared times 1,200 minus x squared divided by 4x. X cancels here. So I have 1,200 over 4 is 300x. And then distribute that with that, I get minus 1/4 x cubed. This is a quantity you want to maximize, and x is greater than 0 again. Right? These are distances. Distances can't be negative. Distance can't be 0, at least to come up with a box. All right, so I think I left you here last time, so let me finish this. Okay, first derivative, 300 minus 3/4 x squared. Second derivative of that is 0. Derivative of that is negative 3 over 2x. That's always less than 0 for all x greater than 0. Okay, you're plugging in a positive quantity. So if I plug in a positive quantity, negative 3 over 2x will be less than 0. Less than 0 means concave down. At a horizontal tangent, you'll have a maximum. Are we looking for a maximum? Yes, we are. Okay, so set v prime equal to 0. V prime was this. 300 minus 3/4 x squared equals 0. clean it up, multiply both sides by 4/3. I want to get rid of 3/4. So get rid of 3/4 by multiplying 4/3 on both sides. So that's a 4/3 curve. You can't see it in red. 4/3, 4/3. 0 times 4/3 is 0. 4/3 times 300 is 400 minus x squared. This factors into 20 plus x, 20 minus x. So x is equal to negative 20. Throw it out. X equals 20. Okay, so x is 20. That optimizes. That will give me a maximum. The y, plug back in here. So 1200 minus 20 squared divided by 4 times 20. If you work it all out, it comes out to be 10. Okay, so the dimensions are 20 by 20 by 10. But answer the question. The question is, let's see where to go. Find the largest possible volume of the box. Okay, so I just find the volume. Length times width times height. So the optimal dimensions to maximize the volume is 20 by 20 by 10. What is the actual maximum volume? 4,000 centimeters cubed. That's the biggest amount of volume that I can have with 1,200 centimeters squared of material. Okay, so that's what it's talking about. Okay. Okay, I only have one more that I was going to show you, and then after that I'll open up the questions. So you can ask me any more questions on 4.7 if you wish, or if you want to go back to 4.3, 4.5, or any previous section, but I know some of those curve sketches might take a while. So I'll just formally lecture on one more. 21. Find a point on the line y equals 2x plus 3 that is closest to the origin. Okay, and we're supposed to do this by techniques of calculus, not by geometry and so on. You can actually do this by geometry, but we don't want that. Okay. So how do I do that? Here's my picture. Y equals 2x plus 3. Here's the origin. Okay, so eyeballing it, it looks like it might be somewhere over here. Okay, I mean, it won't be there. It's not going to be there. It's not going to be down here. The shortest distance would be something like this. So how do I find that shortest distance? Okay, this is a variation of the distance formula. The distance squared is delta x squared plus delta y squared, right? If I kind of expand that picture there. Delta x, delta y, right? Then the Pythagorean theorem says delta x squared plus delta y squared is equal to the distance squared, right? In other words, d squared equals x squared plus y squared. But what's y? 2x plus 3, if I'm on that line, right? So I can write as a function of x now, the square of the distance is x squared plus y squared, but y is equal to 2x plus 3. Okay. So there it is, and that's the expression that I want to try to minimize. Okay. So f of x is x squared plus y squared. Okay. So that x coordinate will minimize the distance. Then I'll just plug back in to find the y coordinate. Okay, so one more time. A squared plus b squared equals c squared. It's a variation of the Pythagorean theorem. So delta x squared plus delta y squared is equal to the square of the distance. Okay. So distance from here to here is x squared. Distance from here to here is y squared. But y is equal to 2x plus 3. Okay. That's, of course, 0, 0. Okay, so f prime, the derivative of this guy is 2x plus 2 times 2x plus 3 times the derivative of the inside, which is 2, chain rule. That's 2x plus 4 times 2x plus 3. 2x plus 8x is 10x plus 12. second derivative, f double prime is 10. That's greater than 0. Greater than 0 second derivative means concave up. So at a horizontal tangent, I will have a minimum. That's what I'm looking for. I'm looking for a minimum. Try to minimize the distance. All right, so all I have to do is set f prime equal to 0. That's easy. 10x plus 12 equals 0. Subtract 12, divide 10. X is negative 12 over 10, or negative 6/5. So the x coordinate over here is negative 6/5. And that does kind of go along with what seems to be our intuition. It looks like it's in the second quadrant, where x is negative, but y is positive. Okay, let's check the y coordinate now. Okay, so x is negative 6/5. Y, well, y is 2x plus 3. So 2 times negative 6/5 plus 3, that's 3 over 1. The common denominator is 5. So I have negative 12 plus 15 over 5, or 3/5. So y is positive, just as we anticipated it would be. Okay, so the answer to the problem is negative 6/5, 3/5. Okay, so that's the one point on the line. Out of the infinitely many points on this line, okay, the point negative 6 over 5, 3 over 5 will minimize the distance. So negative 6/5, comma 3/5. And that's the answer. Okay. All right, that's as much as I had planned for demonstrating for section 4.7 today. So I'll now let you open it up for questions on any section, including 4.7 or curve sketches. I know some of the curve sketches might, take up the whole class period all by itself, but we'll see how it goes. Okay, so let's see. 4.5, number 17 was asked for. Okay, and if anybody else wants to put something in the chat, you may, or unmute yourselves. Let's see how it goes. So 4.5, 17. And by the way, same thing for tomorrow. Tomorrow, I won't lecture that much, if at all. If you just want to do a bunch of curve sketches, we can do that. So 4.5, number 17. Okay. Y is equal to x minus 1 over x squared. Okay. So let me go back to showing the screen. Okay, x minus 1 over x squared. So domain, I'll abbreviate domain with D. X cannot be 0. So all real numbers minus the set consisting of 0. Okay, intercepts. X equals 0, can't happen. Y equals 0. Remember, a fraction is 0 when the top is 0. What makes the top 0? 1. So 1, 0. That's my only intercept. So I will not cross either the x or y axes anywhere else. Symmetry. To do symmetry, you replace x with negative x. F of negative x is negative x minus 1 over x squared. Is that equivalent to the original? No. Is that the opposite of the original? No, it's not. The opposite would be negative parentheses. That would be negative x plus 1. So I don't have that. So no symmetry. Okay, asymptotes. X equals 0 is an asymptote. Okay. So x equals 0, or you can also say the y-axis. So that's a vertical asymptote. VA's vertical asymptote. Vertical asymptote. Then horizontal asymptote, you take the limit as x approaches plus or minus infinity of this expression. And we know that's equal to 0. Okay, so there are plenty of tricks. This is first degree. This is second degree. You know second degree is going to win. Or you can do L'Hopital's rule. L'Hopital's rule will work, 1 over 2x. Or remember there was that trick of dividing top and bottom by x squared, right? We saw that. So any of those work. So y equals 0 is a horizontal asymptote. All right, so we're ready. So y prime, quotient rule. Bottom times derivative of the top, which is 1, minus the top, x minus 1, times derivative of the bottom, 2x, all over the square of the denominator. What is x squared squared? X to the 4th. Okay, let's see if we can clean this up a little bit. X squared minus, let's see, 2x squared minus a minus 2x, so plus 2x. I think that's right. X squared minus 2x squared, double negative plus 2x. Okay. So how about I write that as 2x minus x squared over x to the 4th. Factor out an x. 2 minus x. Cancel this with this. So 2 minus x over x cubed. So you want to simplify as much as possible before you take the second derivative, right? Because that's probably going to get messy. That's my y prime. Quick note, can you tell right away what makes this expression 0? 2. Right? Okay, but we'll worry about it when we get to it. Okay. Second derivative. So I have to differentiate this. Let me just copy this since I got to go back up the paper. Y prime equals 2 minus x over x cubed. Okay, double prime. Bottom times derivative of the top, negative 1. Minus the top times the derivative of the bottom, all over the denominator squared. What is x cubed squared? X to the 6th. Okay, clean it up. This is negative x cubed. There's too many negatives here. Let me play the trick of making that a plus and turning that around. Okay. Negative 2 minus x is the same as positive x minus 2. Okay. And then I'll distribute negative x cubed plus, let's see, 3x cubed, is that right? Minus 6x squared over x to the 6th. So that comes out to be 2x cubed, right? 2x cubed minus 6x squared over x to the 6th. And that means I can factor out an x squared. You can factor out a 2 also, but it doesn't really help that much. I definitely want to take out the x squared because I want to partially cancel that. So we take out x squared, I have 2x minus 6. So unless I made a mistake, I think that's what I got. Double check. Okay, so cancel, cancel. 2x minus 6 over x to the 4th. Okay. So we're ready. Set y prime equal to 0. We just talked about it. Here it is. 2 minus x over x cubed equals 0. X is equal to 2. I'm going to have to plot it. So 2 comma 1/4. Okay. And I don't have enough room here, so I'll have to go back up. So on my sign chart, I lay down my critical numbers, x equals 2, but I also have to put down undefined values, namely 0. Okay, so on my number line, I'm going to lay down a 0 and a 2. So y prime was equal to 2 minus x over x cubed, 0, 2, like so. Okay, pick something here, here, and here. Negative 1, 1, and 3. Fraction bar, fraction bar, fraction bar. That fraction bar matches that fraction bar. Okay, negative 1. 2 minus a negative 1. Positive. Negative 1 cubed. Negative. Positive divided by negative. Negative. Plug in 1. 2 minus 1. Positive. 1 cubed. Positive. Positive divided by positive. Positive. 3. 2 minus 3. Negative. 3 cubed. Positive. Positive divided by negative. Negative. Positive. Negative. Okay. Decreasing, increasing, decreasing. We are doing the first derivative. So intervals of increase and decrease. F is decreasing, negative infinity to 0, union to infinity. F is increasing only between 0 and 2. Now, you might be tempted to say I have a minimum here, but I don't, because x equals 0 is not even a point on the graph. X equals 2 is a point on the graph. And what kind of a point is it going to be? Maximum, right? 2, 1/4 is a relative maximum. Right, then I do my second derivative analysis, do the same thing. Set y double prime equal to 0. Where is my double prime? Over here. Okay, not too bad. When is a fraction equal to 0? When the top is 0? What makes the top 0? 3. Three comma. Let's see. 3, 2 over 9. .22, 0.25. Because I'm going to have to plot it in just a second. Do my sign chart for y double prime. Undefined at 0. We already know that. And where do we get the second derivative to be 0 at 3? Okay, negative 1, 1, 4. Fraction bar, fraction bar, fraction bar. Okay. Now take a look at this. What do we know about x to the 4th? Always positive, unless you plug in 0, and we're not plugging in 0. So positive, positive, positive. That's for the denominator. So numerator, negative 1. 2 times negative 1 minus 6, negative. Negative divided by positive, negative. 1. 2 times 1 minus 6, negative. Negative divided by positive, negative. 4. 2 times 4 is 8, minus 6 is 2, positive. Positive divided by positive, positive. Second derivative negative, concave, down. Second derivative positive, concave, concave up. So the function is concave down, negative infinity to 0, union 0 to 3. Function is concave up, 3 to infinity. Again, 0 doesn't qualify as any point because I don't have a point at 0. But I do have a change in concavity here. So 3 comma 2/9 is an inflection point. Okay, so how do I graph this crazy thing? Vertical asymptote, y-axis. Horizontal asymptote, y equals 0, or x-axis. So my asymptotes are here. And here we already know that. Intercept at 1, 0. So here's 1, 0. A maximum at 2, 1/4. This is definitely not going to be the scale. 2, 1/4. Max. 3, 2/9 is a little bit below that. 3, 2/9 is an inflection point. Okay, decreasing concave down. And by the way, let me just go ahead and plug in some negative. If I plug in, let's say, -1, this quantity is negative, right? And it's over here. Okay, let's see. From negative infinity to 0, decreasing concave down, asymptote, asymptote. Like that. Now what happens? Increasing from where to where? 0 to 2. Concave up from 0 to 3. Okay, asymptote touches here, maximum. The rest of the time, the function decreases. Where'd it go? Right. Decreases from 2 to infinity, but it doesn't drop down all the way here. Okay. We know it approaches the x-axis as an asymptote. Y equals 0. So it gets like that, decreases, concave down to the inflection point, the rest of the time, concave up. So there's our graph. So that's everything. You definitely see there was a lot involved there. Okay, and this should be recorded so you can look at it later. Okay, so let me check that. Okay, so let me get a note of what else people asked for. I'm not sure I can get all of this. 4.1, 13A and B. 17, what is the graph? 41, 55, 57. Okay, so I think I have that. We have about 10 minutes. Okay, let's see what I can do with that. So it looks like 4.1, 13A, B, 17, which does the graph look like? And 41, 55, 57. Okay, let me see what I can do there. First thing I have to do is get back to sharing screen. Okay, 4.1. (13) A and B. Okay, see what I can do with that. Sketch the graph of a function on -1, 2 that has an absolute maximum but no absolute minimum. 4.1, 13A. So it must not be continuous. Okay. If you have a continuous function, you have to have an absolute max and absolute min. So let me write down -1, 2, absolute max, no absolute min. -1, 2. All right, so how do I make it so that there's no absolute minimum? Well, I could, for instance, just let it drop down to infinity somewhere. Okay, so let's make that an absolute max. Drops down like that. And then the rest of the time, maybe just do something like this. That'll do it. That's an arrow. So it's defined everywhere. It's defined from -1 to 2. Absolute max just goes down forever. But you do want a function value at 0. So just connect it like that. Okay, so there's an absolute max, but no absolute min. Okay. B. Discontinuous, but has both an absolute max and an absolute min. Okay, so just have an absolute max, absolute min, but have a break in the graph somewhere. So maybe I'll start off with a maximum and minimum. Okay, maximum, minimum, absolute max, absolute min. Then in between, just have a break somewhere. So maybe go like this. Maybe I put that too close. It's supposed to have a little bit lower. So absolute maximum, absolute minimum, but there's a jump from there to there. Okay, so that would be 13b. Okay, 17, f of x equals 1 over x. It says x is greater than or equal to 1. Okay. Let me lose the book. Okay, so you should already be somewhat familiar with the graph. But if not, x is greater than or equal to 1. So what do you get when you plug in 1? 1. Bigger than 1. 2, 3, 4, 5. Be 1/2, 1/3, 1/4, 1/5. Looks like that. So absolute max at 1, 1, and also local max. And it looks like there's no minimum. If there's no one number you could say is the smallest, even though it's bounded by y equals 0. But you can't say one number is the smallest. You can't say 0.00001 because I can add another 0 in front and it's even smaller and so on. Okay. 41. Two cosine theta plus sine squared theta, 4.1, and only ask for the critical numbers. Yeah. So we don't have to graph it. So f prime, derivative 2 cosine is -2 sine theta. Derivative sine squared is 2 sine theta cosine theta. And I set that equal to 0 for critical numbers. I also have to check undefined, but this is never undefined, so looks like we're good on that front. So let's factor out 2 sine theta, parentheses, -1 plus cosine theta equals 0. If I did that right, let me double check. -2 sine theta. Yeah, that's okay. So that means sine of theta equals 0, or this equals 0 means cosine theta equals 1. Think to my unit circle. Sine of theta equals 0. Y coordinate is 0. That's there and there. Cosine of theta is 1. That's there. It's already covered. Right. Cosine of theta, x coordinate is 1. That's covered by this. Okay, and I want to keep going back and forth. So theta is a multiple of pi. That's 0, pi, 2 pi, 3 pi, 4 pi, or negative pi, negative 2 pi. So theta is k times pi, where k is an integer. So all of these would be considered critical numbers. Okay. And almost out of time. Do I have time for 55, 57? I'm afraid I don't have time for those. Okay, so I'll have to stop here, it looks like. All right. And let's see, anything else quickly in the chat? I guess not. And Prasanna, thank you for helping. Okay, I think we'll cut it off here then, folks. So tomorrow, be ready for lots of questions and answers also, if you want. My lecture will probably be very short. Friday, I'll probably let you have the whole class period for a quiz. All right, that's it for today, folks. Have a good afternoon. See you tomorrow. Bye.
Thank you, Professor.
Thank you.